Welcome back. This is chapter 6.2.4. In this chapter, we'll do DTFT and some applications. And the applications we are mainly interested in is how to use DTFT for Fourier analysis of steady-state response of a system. We also compare the steady-state response with the calculation of the output using difference equations as well as using Z-transform. We are first given this difference equation, and remember when we are given a difference equation in the Z-transform, this is what we have done. I'll now show you the slides in Z-transform for this very similar problem. The slide you should be looking at is at chapter 5.4.5, page 27. In the slide, if you recall, we are first given a difference equation, and then we can perform Z-transform on it. And finally, we find hz, the system transfer function. We'll also be doing that, and you realize that today we're going to follow this arrow, which we let z equals to ej omega to get the frequency response. We're trying to get the frequency response of the system. Alternatively, the other way to get it is we get from the difference equation, we generate the impulse response. How we do that, if you remember, is we send an impulse, x of 0 equals to 1, and x of n equals to 0 for the rest. We send this and compute the difference equation to get the impulse response, and the impulse response is of course aperiodic, and we will take the DTFT, the discrete time Fourier transform, to get h of ej omega. So in this slide, we write it as h ej omega, but we can also write it as this way, because omega, in here, in this particular case, is like this. Okay, that's the idea. And this is the DTFT of the impulse response. Or we can say that this guy is the frequency, frequency response of the system. So today we are going to go through the difference equation, the Z-transform to get h ej omega, and then we'll make use of this. So let's go back to our slides in chapter 6. So we begin with this equation, and what we are going to do in addition to finding the frequency response is this. We're basically going to give you the input to the system. So we're going to give you xn. And in this particular case, we're given a step function and a cosine with omega equals to 0.1 pi radian per sample. That is causal. So we're going to send this xn into this xn, and outward comes the yn. So we should actually write it as this if we want to implement this, plus 0.5 y of n minus 1. We'll always assume that the system is relaxed. That means at time n equals to 0, yn minus 1 equals to 0, and xn is this equation over here. Okay, so the word relax is used here. Relax basically means that the memory of the system is 0. Here the memory is only this variable. Now we're going to use all these 4 approaches using frequency domain through Fourier analysis. So basically we're going to calculate h of omega, and using h of omega we're going to find y omega, and then we can find yn. That's the idea. The other thing is we are going to use the MATLAB FV2, which we have also done it in the Z-transform. And the other one is we're going to use the difference equation. Basically, we're going to use this equation and code up a for loop to generate yn for all the different xn. And finally, we are also going to use the Z-transform, and we will show you the transient versus the steady-state response given by the Z-transform. Now, the interesting thing that you will begin to understand is that the Fourier analysis gives you only the steady-state response. Steady-state response, while the Z-transform here give you the transient as well. and of course the steady state. Alright, so this is a key difference between Fourier analysis and using Z transform for the analysis of the response of this system. Now if you use FV2, you're basically using Fourier analysis. And if you write a code to simulate the difference equation, you're basically getting the same result as a Z transform. Okay, let's proceed.